So last time we did set up a command buffer and started submitting it to the GPU. It's still empty, but at least now it exists, right? And ready for recording some commands. So let's try to fill it with something useful, shall we? As I mentioned, I'll be using Vulkan dynamic rendering feature, which was an extension for a long time, but nowadays it's part of the core since version 1.3. And what does it allow us to do? Well, before dynamic rendering, you would have to do even more setup to do the most basic things. You would need to define render passes that you have in advance, save them somewhere, and you would also need to create frame buffers for rendering. It was kind of annoying and even more verbose than what we have now. But with dynamic rendering, it's still quite verbose to be honest, but it's at least more straightforward. And as the name implies, it's dynamic, so you don't have to set up a lot of things in advance. You can just configure it dynamically during your rendering. So this is what we're gonna do. And the idea is that you create your render passes dynamically using these begin rendering commands, right? Command begin rendering that we record to the command buffer, and we need to supply the rendering info there. So let's start with that. Right, so I have basic rendering info structure here. Let's also add end rendering while we are at it. And between those, we can actually do some drawing commands. So interestingly, even though nowadays it's part of the core, we still need to enable the feature explicitly during our device creation. So let's do that. And by the way, you'll get the validation error about this. So if you try to use CMD begin rendering, it will say that dynamic rendering is not enabled. So how do we enable it? Well, we do this by extending the device create info and providing some additional structures with the features that we want. And there is one handy structure that allows us to configure all the Vulkan 1.3 features with a single structure. And it's called exactly like this: physical device Vulkan 1.3 features. And here we can see the field dynamic rendering. We just need to assign true to it. Now let's do the same next row pointer dance as we did for instance create info extension. So let's define a row pointer. And what we can actually do, because we don't really need a local variable with these features, we just want to extend the device create info, we can simply create it directly and assign a pointer to it to the next, and also assign its own pnext to the next. So if we add something in between, it will be chained basically, right? So this way we can add multiple structure extensions. Now let's add the final next pointer to our device create info and see if the error is gone. And yes, definitely this should be just an assignment, not a variable declaration. And as you can see, that error is gone. Now it basically complains that our rendering info is incomplete. So let's go back to that. And let's see what the structure allows us to define. So right away we can see that it allows us to configure multiple color attachment, a depth attachment, and a stencil attachment. So this would be the attachment for our shaders to work with, right? Like the fragment shader would output colors to the color attachment, and the depth will be written and tested, and the same with stencil if we specify those. Then we of course can specify the render area, the number of layers that we are rendering onto. Since we'll be just rendering on our swap chain image, we have just one layer here, right? So this will be just one. The view mask is, I believe, for the multi-view rendering, so for VR and stuff. And then there is the rendering flags. So let's take a look at those. And I can't actually say much about those because this seems to be quite an advanced features, like resuming and suspending render passes, and also dealing with nested command buffers and stuff like this. So thankfully we don't really need to dive into those. The more interesting thing is the attachments. So let's take a look at the structure. It's right here, right? So here it's actually where the most interesting stuff is, right? So for each attachment, you would specify an image view, and an image view is, well, a view to an image. Basically, image is the actual image data on the GPU, and the image view is a representation of basically a way to access a specific part of the image in a specific way, let's say. We will create the image views for our swap chain images, for example, so we'll get back to it. Then there is an image layout, and the images are actually laid out in the GPU memory in an implementation specific way, and we don't really know how exactly, but the thing is, different operations require different image layouts. For example, we already saw this error, right, that for presenting, the image must be in this present source layout, right? So this is what image layout is responsible for, and there's quite a lot of them. The most interesting ones are color attachment optimal, for example, and this is, well, an optimal layout for using as a color attachment, so for drawing pixels. Then the transfer source and transfer destination. So if you want to copy images or bleed, for example, right, we would need one image in source and another in destination. Another important one is this present source. So basically, after drawing, the image should be transitioned from the color attachment layout into present source layout. So for the drawing operation, we will need one layout, and for presenting, we need another layout for the GPU to work efficiently. So this is a whole huge topic, actually, that we'll get back to. And then let's see. These three results have to do with multi-sampled anti-aliasing, so MSAA. We can ignore this for now because we just want to draw at least something, and we will care about anti-aliasing much later. And then we have the load operation and the store operations. So basically what to do when starting the render pass and what to do when the render pass is finished, right? And for example, on load, we can just load the image, or we can clear the image. So if it's a color image, we can clear it with some color, actually, that we can specify here in the clear value. So, right, we can specify the color. And if we want to clear a depth image, then we would specify this depth stencil value, right? And for storing, also we can specify that we either want to store it for further processing or presenting maybe, or we really don't care what will happen to it. So the driver is basically free to do something that it considers optimal and good for this image. So if we take a look at this, we can see that we are actually not that far away from at least clearing our swap chain image with some color. We just need to create the image view, take care about image layouts, and set up some color in the clear value, right? So let's do that. Alright, so because we need image views to create attachments, we will need to create those for our swap chain images, right? Because we want to draw directly onto swap chain images for now. That means that our swap chain structure will need to be extended to also have image view handles, something like this. And now let's go to our create swap chain procedure. And basically right after we get the swap chain images, let's create views for them. Let's allocate a persistent slice of image views for each image, so we reuse the image count. Let's iterate over the swap chain images and create a view for each of those images. Predictably, we need to use the vk create image view procedure, apply the device to it, apply the create information, allocation callbacks, and the storage pointer. That will be a pointer to an array slot in our swap chain image views, right? Wrap the call in vk check, create the basic image view create info structure. Let's see what are those errors. Okay, this is just some copy paste. Let's go back and fix it. This is of course image view, not image. Now let's see what do we need to pass to this image view create info. So the flags seem to only contain some extension stuff that we can safely ignore. Then we of course need to specify the image for which we are creating a view. So that would be our swap chain image in question. Then we need to specify the view type. And the view type is basically, is it a one-dimensional view or two-dimensional? So how do we treat our image, right? And this needs to be compatible, of course, because like if you have a, for example, 2D image, so it's not layered, then you cannot create a image view of 3D, right? Vice versa, I believe is actually possible. So if you have a layered image like 2D array or just 3D image, you can create a 2D view to have a slice. I think I never tried that, but that sounds logical. But anyway, for our swap chains, we are of course using just a simple 2D images. So this would be this D2, just like this, right? Now for the format. So we do have the format for our swap chain image, right? And theoretically, you could reinterpret your image using some different but compatible format, and sometimes that is useful. But of course, we don't need that complexity. We will just specify the same format as we use for an actual image. So that would be our surface format that we use for the swap chain creation information, right? Just like this. Now this components is basically for remapping the channels of an image to a different channels of the image view. So if you have an RGB image, you can remap it to BGR or something like this using this components wizards here, right? So for each of the channels, you can specify basically which channel to pick, right? Now, if we leave this as the default 0 value, that should go to identity, so it would be just a one-to-one mapping without any remapping. Now the sub-resource range is interesting as well. Let's take a look at it. Basically what it allows you to do is select so-called image sub-resources. So for example, if you have an image and you generated MIP maps for it, then that will contain multiple levels, right? Your image will contain different MIP levels, and your image view can basically take just a portion of those. And it's the same with the layered images. This is, of course, a bit more advanced, so this is something that we will not use, but we still need to specify at least one level and one layer, even if our image only have one level and layer, which is of course true for our swap chain here, because there's no MIP map for swap chain images. That doesn't make much sense. And we only have one layer because we are not doing any stereoscopical rendering and whatnot. Now this aspect mask is actually always a bit confusing. So this is a bit set of different image aspects, right? So if you have just a color image, you would have a color aspect. For depth and stencil, you would of course use depth and stencil. And I believe this is for much more advanced usages that we don't really need to learn right now. But again, if we take a look at the spec, that will guide us a little bit. It will say that the aspect mask must only be the color, depth or stencil if the format is color, depth or stencil respectively, right? So basically, if we have a color image, like our swap chain image, we specify color. If we have a depth image or stencil image, we will specify, well, depth and stencil aspects, right? So this is basically all we really need to know for now about it. And that should be enough for us to specify the sub-resource range. So the aspect mask is color, base MIP level and array layer can be 0 by default because we'll be not using any offsets because, well, we have anyway just one level and one layer. We will just specify the level and layer count as 1 like this, and that should be enough. Now we do not destroy the images explicitly because those are owned by the swap chain, but the image views is something that we create explicitly, and we of course need to destroy them specifically as well. So let's add some destruction here. And the destruction is of course very simple, right? For every image view in swap chain image views, we just invoke destroy image view, the device, the image view, and the allocators. And I almost forgot to delete the slice as well, because this is what we're dynamically allocating here, so we also should delete it, right? Just like this, just like all the other slices that we have. Alright, now let's go back to our render loop. Let's open the render info and attachment info to the side so we can orient ourselves and start filling out our render path information. So flags we can ignore. So the render area is basically a rectangle where we want to render, and we want to render on the whole screen. So the offset can be 0, but the extent, well, that should be, of course, our width and height of our swap chain image, right? And I don't think we save it anywhere. So let's maybe add width and height to our swap chain structure as well. Just like this, right? U32. Now let's store them in create swap chain. Maybe right after we get the frame buffer size, we can store it, convert it to U32. And now we can replace those width and height actually with our stored ones, so we don't convert it for the second time, just to make a code a little bit nicer. And now we can specify the width and height. We can simply say width and height like this. On the second thought, let's maybe also be explicit with the 0 offset, just so we can better see what's going on. Now, the view mask, as I mentioned, that's irrelevant for us right now, but the layer count is something that we have to specify. And we have just one layer, so we specify 1. And now we just need to specify our single color attachment, right? Because what we want to do for starters is clear the swap chain image with some color. So color attachment 1. And for the pcolor attachments array, let's just point it to a local variable for the rendering attachment info structure that we will create right now. Just like this, right? Color attachment. We need to specify an image view, and the image view is the one of the views that we just created that are stored in our image view slice. And the index is, of course, the image index that the acquire next image KHR function returned to us. So this would be the view to the image that was just acquired. Something like this, right? Now for the image layout, since we are using it as a color attachment, it only makes sense to specify the color attachment optimal layout here. I'm not even sure why do we really need to do that. And by the way, nowadays there's also this generic attachment optimal that you can also use, and I believe that will be context dependent. So if it's a color attachment, that will be color attachment optimal. If it's a depth attachment, that will be depth attachment optimal, and so on, right? But let's stay very explicit. Let's just use the explicit color attachment optimal layout. Now, as I mentioned, resolve mode we can ignore. This is for MSAA. Now for the load operation, we want to clear it, right? So let's specify clear. For the store operation, we want to store it because right after our render pass, we want to keep the data there for presenting. So we want to store it. Now we can specify a clear value. We need to specify the color there because, well, it's a color attachment. And the clear color value is actually interesting. So you can specify colors as float32, int32, or uint32. And this depends on the format of your image, right? If you remember that we are using one of those, BGRA8, and this prefix unorm or also sRGB for the gamma correction. That means that the values are floating point values, but also there are these uint and sint, and if your target image format is one of those, you will use corresponding int or uint fields here. So we are gonna use float32, and this is just 4 floats, and these 4 floats always map to RGBA. That doesn't depend on the real format like BGRA for the swap chain, it will be automatically converted. And just like with the shader output, also with regard to gamma correction, if the target image format is in sRGB format, that means that the color values that are expected to be written to it should be in linear format, right? So without gamma correction. But let's do some stupid color like plain red, right? So that would be 1 for red, 0 for GNB, and we can specify 1 for alpha, although that doesn't really matter for the opaque output. So let's run our application and see if it's red, right? And well, it is indeed red, but our console is still full of validation errors about the image layout, and I'm actually surprised that there's no error about that the image layout is actually not color attachment optimal, even though we are using it as a color attachment, because we never specified that our swap chain images should be in the color attachment format. Maybe that's just something that the driver does for us, or maybe it's missing some validation check, I'm not sure, but we should definitely be explicit and transition the images into correct layouts. So I think this is something that we are gonna do in the next video, so stay tuned.